Welcome back to part 2 of our forest hydrology unit. Our learning objectives for this unit are to explain the changes in water availability that follow the removal of forest cover and explain the potential impact of flood flows. The connection between forest management and water management is often very controversial, and as a result, there's a lot of mixed messaging out there. This screenshot just shows some examples that came up from a Google search on trees and water management. Most of these suggest that trees will reduce available water, although one implies it is a good thing and one implies it is a bad. More specifically, here are 3 examples of headlines that tie flood risk to deforestation. While these articles argue that these are just examples of humans wanting to blame someone else when things go wrong, in this unit, we will briefly explore the fact and fiction behind some of these claims. Let's start with what we know and what is generally agreed upon. Many field studies have looked at the impact of tree removal at a local scale. This involves installing sensors and lysimeters in individual fields that have been harvested and comparing the results to similar sensor arrays in nearby forested environments. So through direct measurement, we can confirm that when you cut down all of the trees, the annual total evapotranspiration goes down. Any increase in direct soil evaporation or understory transpiration is not enough to replace the decrease in transpiration and interception evaporation from the trees. That means that on average, more precipitation reaches the ground surface. The impact on runoff pathways is less clear. Certainly, there is some potential for increased local compaction and decreased infiltration capacity depending on the harvest method. Some locations rely on tractor yarding and burning the underbrush or even tilling the soil post-harvest to prepare for future planting, which can have a much more substantial impact on infiltration than locations that hand harvest and use a concentrated staging area. We also know that more snow will accumulate on the ground when it is not intercepted by the trees, and it will melt faster when it is not shaded and sheltered by the trees. We can see this impact on snow accumulation and melt in observed plot-scale experiments too. This graph shows results from the cut tree experiment mentioned in part 1. The middle graph shows the snow water equivalent of snow on the ground for a clear-cut forest, the black line, a shelterwood forest, red line, and for an area with a mature forest canopy, the green line. We can see that in January 1998, more snow accumulated in the clear-cut and shelterwood forests, with accumulation looking very similar for these two. But during a mid-season melt that occurred around February 1st, there was much greater melt in the clear-cut forest. Following this event, snow continued to accumulate in all 3 experiments, but the shelterwood cut ended the snow season with the greatest amount of snow on the ground. As a result, during the rapid melt that occurred in late March, there was the most outflow from the shelterwood forest. At the small watershed scale, field studies ideally involve monitoring a control watershed that is left fully forested and also monitoring treatment watersheds that are harvested, such as the experiment at the H.J. Andrews Experimental Forest described in our in-class assignment. These types of studies show that there is a consistent increase in summer and annual water yield following forest harvest. That is, as a direct result of the decrease in annual ET, the average stream flow increases and there is more water available to downstream ecosystems. The confusion and controversy comes in when we start to talk about extreme conditions, not average. What happens during the floods? Well, our field studies consistently show that peak flows are higher for smaller flood events, especially those that occur following a dry period. But for larger floods, the results sometimes conflict. In part, this is because there just aren't that many of the paired watershed studies that are able to completely isolate the influence of forest harvest. So the fact that we more clearly observe an impact of forest harvest on smaller storms makes a lot of sense. The differences in transpiration mean that the soil in a clear-cut field will be drier at the start of the rain, so more rain can infiltrate. For a smaller storm, a larger fraction of the precipitation can infiltrate before the clear-cut soil is also saturated. In addition, for these soil moisture differences to persist, there needs to be dry weather to evaporate the water. For really large storm systems, there's not drying between pulses of rain, so soils can remain saturated both in forested and clear-cut areas. Finally, interception in a forested environment can also play a substantial role, but just like the soil moisture storage, the effect will seem larger when the total amount of precipitation is less. Because we are limited in the number of locations that can be set aside as experimental treatment and control watersheds, we often rely on model simulations using high-resolution hydrologic simulation models to quantify the potential impact of land use change. So I'm going to share results of model simulations for the Deschutes River Basin in western Washington. This entire basin is part of a commercial tree farm. Sub-watersheds in this basin have harvested areas that are between 15 and 99% of the sub-basin area. Model simulations using the distributed hydrology soil vegetation model showed an increase in the mean annual flood between 4 and 18% across these watershed areas. The impact of harvest in the Deschutes Basin is shown in a different way on this graph. Each of the blue dots in this image represent a different one of the 10 subbasins that was simulated, each of which has experienced a different rate of harvest. This graph is comparing the simulated increase in a 10-year return period flood to the simulated increase in a 2.3-year return period flood, a relatively small flood event. All of these changes are positive, showing that for all watersheds and both storm sizes, forest harvest increased flood magnitude. But as a percent change, the percent change of the 10-year flood was smaller than the percent change of the 2.3-year flood. That's why all of the dots are below the pink 1-to-1 line. This reinforces the idea that impacts of forest harvest to flood flows are more pronounced for smaller floods. So we know from observations and model simulations that if we cut down the trees, the amount of water that reaches streams each year will increase. We also know that particularly for smaller return period events, peak flow rates increase due to forest harvest. The next thing we want to discuss is the role of snowmelt, in particular in increasing peak flows. This illustration shows the simulated impact of forest harvest on snow accumulation and melt for Hard and Ware creeks, two of the subbasins of the Deschutes River Basin shown before. The maps are showing the difference in simulated snow water equivalents for a model scenario with clear-cut harvest minus results for a simulated control experiment with all mature forest between February 4th and 10th, 1996. On February 4th, the difference in snow on the ground is all positive, showing that there was more snow on the ground in the clear-cut simulation. Over the next few days, a series of wet, warm weather events moved through and snow melted rapidly. By the end of the event, on February 10th, there is less snow on the ground, showing that more snow melted during this event in the harvested area, with the simulated result of a greater flood peak downstream. The last factor that has received a lot of investigation at the watershed scale is the impact of forest road networks in routing water differently to the basin outlet. Forest access roads generally precede forest harvest and forest catchments in order to provide access to the timber for harvest. As you can see from this photo, in mountainous environments, these access roads are cut into the mountainside. There are not great records of these road locations, but we can determine based on published data sets that the density of roads increases with the cumulative harvested area. So we know that where there is harvest, there are forest access roads. Because the roads are built into the side of the mountain, they have an exposed cut slope that intersects interflow pathways, as shown in this inset photo. This means that the subsurface water that emerges from these cut slopes can be diverted into roadside ditches that then drain directly to surface drainage networks. This transition can decrease travel times to the watershed outlet, increasing peak flow rates. To see this impact at watershed scale, we once again turn to model simulations for Hard and Ware Creek and the Deschutes River Basin. Here the blue line shows model simulations when the forest road network is represented. We can see that compared to the control simulation with no forest roads, the hydrograph peaks higher and a little bit earlier when roads are represented. Unlike with the case of forest harvest alone, the impact of forest roads has the potential to increase with increasing storm size. So where does that leave us? We have multiple points of evidence based on small-scale, field and small watershed observations and simulations. But when people look for impacts at large watershed scales, the results can still be contradictory. How can that be? Well, for one thing, when we are dealing with a large watershed, people live and work in these watersheds. It is impossible to control them as an experiment, so there is mixed land use involved, and forest harvest only occurs in part of the watershed. In addition, as we discussed in our watershed characterization unit, forest harvest and road building may result in changes in the timing of runoff generation, but depending on where that occurs in the watershed, the change in timing could decrease the synchronicity of the hydrograph at the outlet, leading to surprising results. And a final caveat, the field evidence I have presented today all came from mid-latitudes. Impacts may be different when looking at depleted tropical soils. So in summary, we know that forest harvest can locally increase the amount of water in rivers. Through ET changes alone, average annual runoff will increase. However, this water will not always come when it is needed. Because of changes in flow pathway, resulting in more surface flow and less inner flow, as well as changes in snowmelt, more of this water may come out during storm events. Forest access roads play a role in these changes by increasing the hydrologic connectivity of mountainous forested environments. This concludes our unit on forest hydrology. You can now complete the forest hydrology Quizlet to reinforce these concepts.